spin-orbit coupling. So you're, for this, to find these eigenenergies, you're perturbing the Hamiltonian by adding the spin-orbit coupling term, right? That third term. So that's your Hamiltonian perturber, if you like, right? So you get different eigenenergies because you're using a different Hamiltonian. Now the difference between these, strong field alone, and this is the strong field, well, not so strong, plus the spin-orbit coupling term gets involved in the Hamiltonian. Right, and the difference between those is from this theory, from first order perturbation theory. Now this will just be mysterious. You won't know where it comes from because you haven't done the theory yet. But you just have to accept it for the moment, right? So this is what you get as the error correction, the energy correction, if you like. The difference between the strong field energy eigenvalue and the energy eigenvalue that you get when you add the spin-orbit interaction term to the Hamiltonian for this one. Alright, now this delta term, this difference in the energies between the strong case and the strong case plus spin-orbit, you can rewrite this in terms of the spin-orbit splitting energy that we did earlier. In this, written out the formula again. You've seen this before, it's just revision. So we can rewrite this in terms of this. And it turns out to be this. Okay? So this is like a correction in the energy eigenvalue, and we can add that, and this, you may ask why. Well, it comes out of perturbation theory. So again, you have to study chapter 10, right? So at the moment, again, it's just being thrown at you. So you can just add this correction term of the eigenvalue of the energy, this delta correction term. So just add that to the energy eigenvalue of equation star, which is this here, right? E, NML, MS, well here it is, yeah. So you're adding this correction energy, this term here, okay? Now what else can I say? From two sessions back in the splitting diagram that you saw, on the right hand side of that session, there were a column of values, ML, MS, and then I said you wouldn't understand what they're about. Now this ML, MS, this comes from the first order perturbation theory, and here's your term ML, MS. Okay, so we got various values for ML, MS. I'll just read them out. You won't see it, but we got values like a half, a 0, minus a half, well, 3 different sorts. So you can plug in here 0, plus a half, minus a half, and they'll change the energy eigenvalues you get when you bring in this correction to the eigenenergies. So and you get this by adding the spin-orbit coupling term to the strong field Hamiltonian Zeeman effect Hamiltonian. Right? Okay, that's the third case, getting more and more complicated. The weak field Zeeman effect is the third case. Now, you assume the energy levels are so weak that effectively your eigenfunctions for the strong form are unchanged. Okay. Now the mathematics is too complex to be dealt with at undergrad level, so you just forget about that. And so instead, I'll just use a sort of a hand-wavy physical type argument to make it plausible. But since I ran out of board, I can only just start on it. And I'll probably repeat this in the next session. That's the thing about boards. They run out at odd, unusual times, right when you're in the middle of something. But unavoidable. All right. So what's to say? So assuming the strength of the magnetic field is so weak that the eigenstates that you got when B was naught, in other words, when the fourth term of Hamiltonian was not there, okay? So we assume the eigenstates for this case remain valid when the field is very weak, okay? Because that's what this third case is about: weak magnetic field, Zeeman effect, right? And so your vector J, the total angular momentum, which is defined as the orbital angular momentum plus the spin angular momentum, L plus S, that remains effectively intact. It doesn't get modified much, right? So you can talk about the component of this total angular momentum projected along the z-axis. So you can talk about your MJs. These are the allowed component sizes of your total angular momentum along the z-axis. So there'll be 2L or 2J of them, right? So you're assuming the components of this J along any other axis other than Z they don't interact. They have no effect on the potential energy of a Hamiltonian, let's say. That might be a big assumption, but let's assume that's the case, right? So no addition to the Hamiltonian due to interaction of non-Z components of J. Right? Said that twice. Hope you've understood it. Okay. So what we're going to do is just setting up the model for this third case, and then once we've finished it, probably just one more session, probably not even that. That's the end of the theory portion of this chapter, and we're getting close to the end of the book, right? Then, so what we are interested in then is you take take a unit vector of this total angular momentum J along the z-axis, and you'll get an interaction term with let's see, where does this come from? Now this L plus 2S, we've done that earlier. Yeah, I think I'll leave this and go into fuller detail once the rest of the details become clear for the next session. Right? So this is the third case of three. They all use the same Hamiltonian. In case one, you assumed the magnetic field strength was so strong you could neglect the third term. It was just dominated by the fourth. In the second case, the Paschen-Buck effect, that's not the case. You do need to consider the third term, and you considered the addition of that third term as a perturbation of the Hamiltonian, where the main contribution of the Hamiltonian was due to the large magnetic field term, the Zeeman effect term, right? And in this third case, that magnetic field term, the fourth one, is considered weak, and the calculations are complex. And then we're just starting here. We'll lead on in the next session talking about setting up a quasi hand-wavy physical model without the mathematics. You know, we just use a sort of physics type argument to make the result, you know, for this analysis of the weak field sound plausible. So just wait till next session.